bipartite graph structure. Okay, there are actually many ways in which you can interpret such a bipartite graph in an insurance context. Of course, you could think of the blue nodes as individuals, and the individuals may have several insurance contracts to primary insurers. So, O1 might have health insurance and a car insurance, and O2 might have household insurance, and this is not necessarily with the same company in each case. But we don't want to think in terms of individuals and primary insurers, but we rather want to think in terms of big losses. That means we shall consider the objects to cause big claims, heavy-tailed claims, and in that framework it is more sensible to think of the orange nodes not as primary insurers but as reinsurers. Oh, hi.
Sorry.
Oh, no problem. I can just wait a minute. I just started.
A lot of food in this room. Did you see anybody else?
Oh.
No.
Okay. I was just explaining this graph model. We have large claims in the blue nodes, and these orange nodes are reinsurance companies. And we have a random graph structure which determines the market contractual relationships. Okay.
What are the blue nodes?
The blue nodes? Yeah, you can think of the blue nodes to be big portfolios of losses. So O1 could be a big portfolio of household insurances in an earthquake region. So within O1, the individual contracts are highly dependent. That is why they are considered in the model as one big risk. And you can think of O2 as a big portfolio of household insurances in a hurricane region. So if O1 is earthquake and if O2 is hurricane, they're rather independent, right? And O3 might be related to some other type of zero risk, like aviation risk. O4 might be a portfolio of life insurances, which might also cause big claims in case an epidemic happens. Okay, so that's what I plan to do today. I will introduce the model more clearly. Afterwards, I give a brief overview on regular variation, especially multivariate regular variation. Having done this, we can give some statements about the distribution of extreme losses in that setting, in particular about the dependent structure of extreme losses among several reinsurance companies. And in the fourth step, we will apply that to several risk measures: value at risk, expected shortfall, conditional value at risk, marginal expected shortfall. And we will find expressions for all of them in terms of the network structure. Okay. So yeah, we start with Q agents, which are the reinsurance companies, and these D objects, which are the objects to be insured. And an agent I chooses actually an object J with a certain probability Pij. And all edges in this bipartite graph appear independently. So that means the market is determined by a random graph, which is inhomogeneous because we allow for different Pij. Okay, and this random graph can be represented just as matrix A tilde of dimensions Q times D. And yeah, the realization belonging to the picture we saw is that one, where agent 1.
Sorry.
Oh, hi.
Sorry for the took me a while to find it.
Yeah, somehow complicated.
Okay.
So actually we have a bipartite graph, Q agents, the objects, and this random graph is inhomogeneous. And yeah, that's all what I was. Yeah.
How do Q and D stand in a specific relation to each other, or can
Not
they
yet.
appear-
So in the first step, we think of finite random graphs, so we don't have to relate them to each other.
But there can be more objects or more agents.
Yeah, of course. I mean, you certainly have more objects than you have reinsurance companies.
Yeah.
Okay. So, and this random graph, so one realization of the random graph, of course, can be represented just by such a matrix of ones and zeros, indicating that agent 1 ensures object J and ensures object 3 and 4, but not 5 and 6. Okay, so before I introduce the extremes on this bipartite graph, I introduce the notation F tilde G. Yeah?
That's something just for to understand the one.
Yeah.
So you said that one could think of the blue areas as insurance events, or
Yeah,
as big, rather independent
Yeah.
events that could occur. So, are you assuming that once companies decide to insure with a certain probability that event, the loss is equally distributed among all people that insure it, or is there?
yeah, I'll come to that point. Yeah. No problem. Yeah. So notation which will appear quite often in the rest of the talk, F tilde G, means that the functions f and g behave asymptotically in the same way as it is stated here. Okay. And to introduce these extremes on the graph, we equip the objects just with random variables that have Pareto-like tails, as I did it here. So to object 1 belongs V1, which scales in fact like t to the power of minus alpha for alpha positive. Okay, and yeah, back to your question, of course, the losses which appear here in object 1 are then, in the first step, equally distributed to all the agents which insure that particular object. Oops. Well, on the laptop it's here.
It's probably just the screensaver.
Oh. No. Okay. So yeah, having said that the losses are equally distributed, I have written down it here in a formula. So Fi will in the following denote the exposure of agent I, which writes in that way. So we sum up overall objects and we divide the claim which object J has by the number of agents which insure object J. This is degree of J. And we just count that, of course, if I has a contractual relationship to J. So that can also be written in terms of the random matrix A tilde. And we can define using A tilde another random matrix A just by the ijth component of A is 1 over the column sum of A tilde in case I is connected to J. And having written that, I can simply state that F, which is the vector of agent losses F1 to Fq, writes as this matrix A, defined here, times the vector of losses of the agents. Okay, and this is quite convenient as we see in the following. Yeah, maybe just an example that it's clear. So that was the realization of the random graph we saw. Then the equals are distributed equally. So what object 1 causes goes 1/2 to agent 2 and 1/2 to agent 1. And we can write f, this realization, in that form. Okay, so that's the picture for that. And in the following, we will look at dependence between f1, f2, and fq in this extremal sense. Okay, and for that I refer to the notion of regular variation. So let me first say what is a deterministic regular varying function. So it just has to fulfill this property. Of course, t to the power of minus alpha always fulfills this property, but you can also multiply other slowly varying terms connected to logarithm or something like that. And as you see, if you take this function, the limit condition holds as well. Okay. And yeah, we're doing somehow stochastic, so we are interested in what is a regular varying random variable, and this is just defined through the tail function. So x.
So what is the intuition of what does being a regularly varying function mean? I mean, I can see the mathematics, but what does it capture?
Yeah, I mean, you can essentially show that every regularly varying function is of that form, where you have, so to say, the t, so this polynomial term, t to the power of minus alpha, times something which varies slowly.
So it's scale invariant, but in the tail.
So
Yes,
yeah,
that's something like this, no? Yeah.
In the tail, it's like a power function.
it's essentially like a power function. But if you compare,
So you look at the t limit, and then you want it for large t to behave like a,
yeah,
a power.
okay. So and a random variable is called regularly varying if this survival function is regularly varying within x minus alpha. Several examples for shear Pareto, something alpha stable, a log gamma, and also Cauchy and student. But in Cauchy and student are two-sided, so you have to adjust the definition for that. Okay, here are two very classical theorems on regular variation of random variables which have direct implications for the model. So the one is by Breimann and actually states that if you have one random variable which is heavy-tailed with a certain index minus alpha, and you have another random variable, say x2, which is lighter-tailed, so denoted here by small o, then the convolution of x1 and x2 is essentially the same tail as x1. So it's the heavier tail which counts. And the implication for the model is that we assume all the object losses to have the same alpha. Because if we didn't, somehow the tails which are lighter would vanish from the asymptotic considerations. The other one is by Breimann, which states that if you have something, a light-tailed random variable and something which is heavy-tailed regularly varying, and you look at this survival function, then you can just put this lighter-tailed thing out with the expectation and the exponent of the heavier tail. And we will actually use a version of Breimann's theorem which is multivariate. So if you have matrix instead of psi here and a vector instead of x here. So, but before we can do that, I certainly have to introduce multivariate regular variation. And this is done in the following way. So you take a random vector x, which has values in Rd plus, and we call its distribution multivariate regularly varying with certain index minus alpha, if there exists a finite measure rho on the unit sphere, so that this type of convergence holds. So here a norm appears. This is the norm with respect to which the unit sphere is defined. And this measure rho is on the unit sphere, and here you should plug in the set you're interested in. So you scale x down to the unit sphere. Yeah, it's a bit technical, but let us maybe have a look at a simplifying picture. So I just set u equal to 1 from the previous definition. And here you have the unit ball, so the positive part of the unit ball with respect to the maximum norm. And you can blow up this unit ball by factor t, of course. And now you have a magenta set B, which somehow lives on the unit sphere here. And what you do is to consider the conditional probability that x is within this blue shaded area, because everything within this blue shaded area scaled down to the unit sphere is in this magenta set B, right? And if you have convergence in T to some measure rho, then rho is the spectral measure, and it will actually determine the extremal dependence structure of the vector x. Okay, here's just another possible definition of multivariate regular variation. So here, this limit measure lived just on the sphere. And it is also possible to define regular variation with a measure that lives on the whole RD+. This is for some technical reasons. I introduce also that. So here we don't scale down to the unit sphere, just put some set in here, and as t goes to infinity, that set is blown up and moved outside, right? And it's scaled with the norm of x greater than t. Of course, this mu also has certain relationship with alpha, which is given here. So if you consider mu with t times d, then t comes out with the index, or with the exponent minus alpha. Okay, and here is this multivariate version of Breimann's theorem, which I came to talk some minutes ago. So we can just take a random matrix here, which is of dimension q times d, and regular varying vector with certain index minus alpha, which has such a limit measure mu. And then we can determine the limit distribution of AX. And this is mu tilde, which is, of course, A is random, so you need an expectation. It's the image measure of mu, which belongs to X by that way. Yeah. And this is will help us clearly to understand what the distribution of our vector f of the losses of the reinsurance companies is, because we have the random matrix here and we just plug in the claims of the objects at this point, right? And this makes it possible to get assertions about the extremal dependence structure. Okay, that reminds me that I should talk a little bit about independence. So in the beginning, yeah?
Can I just ask one thing again about the multivariate definition? So,
Yeah.
would it be like an intuition to say that the multivariate regular varying probability measure is kind of radial symmetric?
Pardon me?
It's kind of radial symmetric probability distribution function in, say, 2 or 3 spaces. If you want to have an in every direction, you have that tail behavior.
Yeah, not only in every direction. Maybe it becomes clearer if I show the example. Okay, so what concerns independence? I simulated 5,000 claims of such a bivariate vector with Pareto and index 1.3. And what you actually see is that the big losses, although this is a bivariate vector, are concentrated on the axis. So here is no mass in the interior, right? Which would certainly not happen if I would have plotted 5,000 normally distributed claims. Then I would have here some elliptical function, right? And I would have lots of mass here, but it doesn't happen with the extreme losses of the Pareto. So you should keep in mind that these big losses are just happen in one component when big losses happen. So that makes it possible to sum up. So as I said, we start with IID, Pareto like object claim variables V1 to Vd, and they all share the same index in the tail. And then we can actually state that our vector f of agent losses is regularly varying with minus alpha, also with minus alpha, and with a certain spectral measure rho. And now the random graph enters this measure rho in the sense I have written it down here, because rho has to be a probability measure. I have some scaling constant which depends on the random graph, and of course this measure here also depends on the random graph by this image measure construction as we saw it in this Basrak theorem. And this mu actually is this limit measure which is related to the object claims, right? And that makes it possible to determine the extremal loss distribution of F and the dependent structure of it just by knowing this alpha, of course, and knowing that norm, which I'm working with, and knowing the law of the random graph. And these three ingredients, of course, the dependent structure in this V also counts. These four ingredients actually determine this spectral measure rho in a particular way. So we will have a look at some examples later on to see how things change in different market situations.
Sorry, I'm a bit lost. All this, network, the distribution on the V's, etc., all affect the extremal measure. That's obvious. But you say in some particular way. So can you tell me from that particular way that you have there, what is special, what is interesting? Because I'm totally...
I see that. So I have collected some examples in the end and made some plots to see how different network structures influence the dependence.
Okay. But presumably this structure that you prove in this theorem will be helpful in that, in understanding those examples.
Yeah.
So, I look at this expression and it doesn't tell me much.
Yes, of course, not yet.
Okay.
So, some things which will turn out to be important are these constants here, as I will show soon. And yeah, we'll have a look at different network situations and different market situations.
Let me ask another question. So, in relation to the graph that you showed right before,
Yeah.
I think it's in the slide afterwards, where you had no realizations in the interior.
Pardon me?
Where you had no realizations in the interior.
Yeah.
So you say that this would not happen if the distribution had been normal, but it happens if the distribution is Pareto.
Yeah, if it's heavy tailed.
Why?
The intuition is that
I would have thought that if it's Pareto, it's more likely that you have.
Yeah,
you
it's
have-
more
you
it's
have-
more likely to have yeah. If you have one-dimensional Pareto, is of course more likely to have
Yeah, large
large losses. But this is the thing: if these two components are independent, then you also have large losses here, but only in one component.
But they are independent.
Yeah,
So then
yeah.
they-
That's essentially, so to say, a special feature of these multivariate regularly varying, or if you take a vector of heavy tails, then and you take all the marginals independent, then you can actually prove that the interior is empty, and that these spectral measures.
If you simulated two independent normals, you'd get a nice fan of points right through the positive quadrant,
Hmm.
because the bivariate normal is not multivariate regularly
Yeah.
varying, obviously. So it is a kind of interesting difference in the properties that if you have a non-multivariate regularly varying distribution like a bivariate normal, you get a kind of even fan of points around the quadrant, but when you have this kind of distribution that he's describing, it's either extreme in one component or the other in general.
It's exactly opposite to what I said. It's not radially symmetric. If you have two normals, you will get a radially symmetric PDF. And you will
Yeah,
get
in
points
the
everywhere.
independent
But
case,
if you
not.
say if you have two normal distributions, you get your probability distributions
Yeah.
is radially symmetric. And here you get like a
Yeah.
flat start, like the NATO symbol kind of
The
PDF.
spectral mass becomes 2-point masses at each unit.
Yeah.
But can you explain the intuition? I have no. There should be an intuition of what's going on. Or there's no intuition that you can explain.
Yeah, I mean there are.
Because it is against my intuition. I mean, perhaps someone in the audience has
Yeah.
have a better intuition because they're more. But I am. It's just contrary to what my intuition would tell me. So then I want to really understand.
Yeah, but I mean, so I like a little bit of some easy intuition. You can just prove that actually, but yeah, I know, but
I think if one realization is really big, what's the chance that the other one is also really big? It's like you're squaring the probability.
No, but this would happen. This would happen whenever the in a bivariate if they are independent. Also, you would have to sort of like sort of squaring. No?
There is
I mean, because this is not. It's
So if you-
sort of multiply.
I mean-
That is the same independently of whether you are talking about the normal or.
Right.
so
So now, why?
Yeah,
There is a fan in between, but it's just not
in the
if you
extreme.
take-
So
if you
it's
take
it's
the
just
axis
in the
0 to 10.
it's just about the
will see-
extremes.
Yeah.
So if you have the
everywhere.
Yeah, it's all kind of concentrated down at zero.
So here happens rather a little bit. So if Pareto losses are rather small, then you
Put
can
it on
have-
a log scale, you see something
yeah.
maybe more intuitive.
No,
Yeah.
I don't know.
So
I mean, you understand this very well. So you should be able to explain not the technical details, which are of course difficult to explain informally, but this intuition of what's going on. Because no, I'm totally. I mean,
I have a question.
Yeah.
If you zoom in on say 0 to 10 and 0 to 10,
Yeah, then
Would
it
it
doesn't
look
look
like
like
this?
so.
would it look like the normal? I mean, it's not the normal distribution, but it
Yeah,
would
yeah,
look
but-
like the normal where it's
It's not the case. So if you zoom in, so you have I don't know 5 here and 5 here, then you might have something like this in this smaller range.
yeah.
But only if it gets to the extreme, you get.
but so let me explain. Let me ask the question another way. You've proven this, okay?
Mm-hmm.
So it has not been magic, no? You have some idea what why you thought it was true in the first place.
I think the intuition is the likelihood of getting a kind of joint extreme hit is just very, very small compared
Yeah.
with the probability
Mhm.
of getting an extreme in one component.
But
or
it happens
another.
for any distribution. And even, and for the, for normals, it will happen even more so.
You're thinking that if you have a two-variate distribution, and if you consider, say, the sum of the squares, that if I put, say, one on the x and one on the y, that should be the same if I put square root of 2 and square root of 2 on both. Because that gives you a vector of length 1, and that should have the same probability. That happens with a normal distribution. Because if you have a normal distribution in x and a normal distribution in y, if you multiply the two probability distributions, it actually gets radial symmetric. So
Yeah.
if I move on a circle, that's the same probability.
Well, but still, the same
That's not the
probability,
case
the
here.
same probability, but very low probability, no?
No, but here it's not the case. So here is the case that, say, the level set of probability is not a circle, but it's like a cross shape.
The level, but these you see, you have simulated claims. You're not really there mapping the levels, you're mapping the distribution.
Can I make a drawing?
Yeah, of course.
You see? It's not the levels that you're interested in, because indeed, you have the levels in this way, but levels corresponding to very low probability, you should not observe them.
If you stand here
Okay?
and you're looking in this direction, then your spectral measure will be, depending on the unit ball, will be something like this. And if you now plot, if I plot this, say, E2, E1, these are the 2 points, and here is the mass. Then for the independent case, you will have a point mass here and a point mass here. And
Rather here, on the axis, in the independent case.
yes, one here and one here.
Yeah, okay.
And you can, for different distributions, so you'll get spectral measures.
Yeah.
And why you see only this and this is because in the independent case, this
Yeah, it's basically,
function
basically.
degenerates to 2 points.
Sure.
So there will not be anything here.
Sure, no, I understand this, but this happens for normals and for Pareto distributions.
No, not for the normal, because the normal doesn't fall into this category of distributions. This is for extreme value distributions.
Ah,
The normal is not an extreme value distribution.
I see. So then, okay, I think I'm starting to understand. Yes, okay.
For the
Yeah,
normal,
of
you
course,
would
we,
have
we,
sort of
yeah,
a-
of course, the normal you have this would not be, okay, I see. Okay, no, I think now I understand, yes.
Okay. So in the independent case, it's concentrated on the axis, and we now put this random graph in front of V, and then something happens, of course. So if you look at the spectral measure, as Eric said, it's concentrated on the points E1 and E2. And yeah, then if we put our random graph before in 3 dimensions, the spectral measure of V was concentrated on E1, E2, and E3, and the random graph somehow now distributes the losses, right? So it's not the case that F1 gets all the losses, but there's a certain probability that F1 and F2 share the losses. And this is why the spectral measure is also concentrated off the axis. So you can, of course, have with a certain probability the case that F1 just faces a big loss, but there's a certain probability that F2 faces a big loss also. And here this is the 0.111 scaled down to the unit sphere, which means just that every 3 face a big loss. Yeah, I just wrote it down here. So the support of this discrete spectral measure now is just every vector with entries of zeros and ones, which is scaled down to the unit sphere, and you can just write the explicit formula, which just depends on the random graph, the alpha, and the norm. And yeah, so now I have the f here, so I put random graphs below, and as you see, you have in 2 dimensions the concentration on the axis, because with certain probabilities that can happen, that just f1 is exposed to v1 and f2 is not exposed to v1, but the loss happens in v1. And yeah, we also have, so to say, mass of the spectral measure on the point 1, 1 here. Okay, yeah, let us.
So this is obvious, no? Or not? I mean, so you have, given what we learned before about the measure being concentrated in the axis. Now
Yeah.
you're looking at the distribution on the f's, which
Yeah.
are convex combinations of this.
Yeah, which are.
So then they have to be.
They have to be, yeah,
they have
that's
to be in the
essentially.
axis and also in some
Yeah, and in higher
linear subspace of the.
Yeah, yeah. And in higher dimensions, you have 2 to the power of q minus 1 points. And this is somehow a feature of the random, it depends on the random graph, because we said we distribute all losses equally. If I would allow for different weights, so if I would say, I could have a convex combination of
Yeah,
the loss.
Yeah, sure.
Then it could even happen that I get a continuous distribution for the spectral measure, right? But because the random graph is constructed in such a discrete way, we end up with finitely many points of mass of the spectral measure.
Mm-hmm.
Okay, so let us have a look at 2 scenarios to make sure that the rho actually does what it's expected to do. So the first gives us the probability for a certain random graph in which agent 1 chooses object 1 and object 2, each with probability 0.9. So he ensures them with quite a high probability, but agent 1 does not like to have objects 3, 4, and so on. Whereas agent 2 rather prefers objects 3 and 4 and so on. So this is a kind of really separated market structure. And in this kind of separated market structure, you expect to have big losses rather in one component than the others. Because if these V's have big losses independently, then it might either hit agent 1 or agent 2 or agent 3, and this is what we see here. So to have just a loss for agent 1 is, so the rho probability of that is 0.3, and this is for all 3 agents, while having a shared big loss which comes through the network in all 3 components has quite a low probability, because the network, which would make it possible to have lots of connections, has quite a low probability to happen. Yeah.
I'll ask later.
Okay. And the other situation is actually, if we look at a totally homogeneous network, so each agent ensures each object with a certain probability of 0.9. So this will be a highly connected market. And in this highly connected market, it is, of course, quite improbable that you have a loss just in one single component. But it's quite probable to have a loss which share all 3 agents. Okay, so questions?
Excuse me, but probabilities are not normalized.
Pardon me?
Aren't probabilities normalized?
Yeah, this row is probability measure. So that means you have 0.3 to have a loss in agent 1 and 0.3 to have a loss in agent 2. This is why I didn't put brackets around it. So if you take this by 3 and this by 3 and of course this by 1 and sum them up, you should end up roughly by 1. Because, yeah, I cut some digits, but it should roughly 1. Okay.
So just if I understand, so if you would take the second case where everything is identical and you would reduce the probability, you would get a shift from the 3 events towards the 1 event probability. Is that?
Pardon me?
If you would put, instead of 0.9, you would put 0.2.
Mm-hmm.
You would get more probability for the single events. Is that correct?
Yeah, yeah. We have a look exactly at the situation later. Okay. Just one more proposition, because we can also determine the probability of joint exceedances in an asymptotical way, independent of the network structure. And we can determine the tail probability of aggregated losses. So if you take any aggregation function on this f, then it scales like that constant times the tail probabilities of the object vector. And for one, it's certainly of interest to look at a singleton here. So what is the probability that fi is greater than ut? And this is just the sum j equal 1 to d, and you have the expectation of aig to the power of alpha over u. And having determined these tail loss distributions, we can rather immediately say something about risk measures, about the asymptotical behavior of this value at risk of a single agent and of this value at risk of the aggregated vector. And yeah, you just use some assertions from regular variation to get the asymptotic statements here. So if the gamma goes to 0, hence the value at risk level goes up 90%, 95%, 99%, and so on, then it scales actually like gamma to the power of -1 over alpha with some constant, and the constant is determined by the network structure. And of course, if this term gets big, it surely makes a difference if you have here 1.5 or if you have here 4.5. The same applies for the norm of f, of course, but you have a slightly different constant here, of course, taking into account that norm. And it will turn out later that only these constants are somehow interesting to study, because they just determine how big is the asymptotic value at risk. We can not only do that for the value at risk, but also for the expected shortfall and get similar formulas. So this is essentially the value at risk, and you get an additional factor depending on alpha. Because this alpha is greater 1, the expected shortfall is also greater than the value at risk in this classical framework. This is not really new, that you can apply these regular variation techniques to these tail distributions, but you can also do that for conditional value at risk. In the sense I have defined it here, so you look at the probability that fi is greater than t given some event which concerns the whole system, or you can look at it in another way around. And having said this, one can surely look at asymptotics like these to get to get a feeling for how much is the value at risk of fi influenced by the value by a rather disastrous event of the whole vector, which depends, of course, of the whole distribution of f. This scales linearly in U. Okay. Another thing you can do is you can define such, it's maybe called marginal expected shortfall or tail conditional expectation, where you look at the expected shortfall of one agent and condition on that all agents together, the aggregated all agents, face a big loss. And again, you can give asymptotics for the expected shortfall in this setting. And now the expected shortfall depends on something deterministic, concerned to alpha, and it depends on a mixture of both. So this multivariate constant and this univariate constant arranging from the network properties. And of course you have this gamma here again. So this expected shortfall is also clearly identifiable through the network structure and the alpha and the norm. Okay, so just to sum up, we have defined the random graph through these probabilities that an agent I ensures an object J, and that gave us this matrix A. And as we saw in these previous examples of expected shortfall and value at risk and conditional value at risk and marginal expected shortfall, the only thing which matters for these tail risk measures are these two constants here. So these two constants we're studying in the following. Okay, so let us have a look at a simple example.
Can I just one question about
Yeah.
the
About the previous formula, or?
Yeah, the previous slide, just to be absolutely sure. So this asymptotic size of value at risk, this is in the limit as gamma goes to 1.
Gamma goes to 0.
Yeah, sorry, gamma goes to 0, yeah, the extreme, right, yeah, gamma
And,
goes
and
to
it
0, yeah.
goes to infinity, this side goes to infinity then.
Okay.
Was that a question, or?
Yeah, no, I was just
Okay.
checking, I understood the tilde here.
Okay, so look at a very easy situation where you have 3 objects and 3 agents, and look at it in dependence of a parameter b. So if b is near 0, then we actually have almost the identity matrix here, which means we have quite a separate market in the sense that agent 1 ensures object 1, agent 2 ensures object 2, and agent 3 ensures object 3. But there is no interaction, no sharing of risk at all. But if this b grows, and it finally approaches 1, you are in the situation of total risk sharing. Now you can study this constant before the value at risk, how it behaves if that b grows. And we find that if this alpha is smaller than 1, the constant actually increases. That means if you have very heavy tails, so if you're in infinite mean model, then this kind of diversification of risk or risk sharing is not what you want as an individual, because your value at risk constant goes up, and this is a bad thing for you. So the black line corresponds to alpha 0.8, while the blue line corresponds to alpha equal 3, which is of course greater than 1. And you see, in the case of alpha greater than 1, risk sharing is beneficial for you because your value at risk goes down in that way. Of course, we can also look at the multivariate constant. So what's the value at risk of the aggregated vector? so the value at risk of the whole system. And again, in this case, alpha 0.8 is the black line and alpha 0.3 is the blue line. Now you can see that both are decreasing. So in the multivariate setting, risk sharing is from that point of view also in all cases beneficial. And here's, now it's not really a contradiction, but so as I said before, in the case of alpha smaller than 1, for the individual agent, risk sharing is doing things worse, but for the system as a whole, risk sharing is better in the infinite mean case. So this is a simple example where the objective of a single agent differs from the objective of someone who cares for the whole system. Yeah, let's have a look at homogeneous. I mean, I should certainly point out something. In this model, every object is insured with probability 1. So from the very start, all the risk which is caused by the objects is paid by the insurance agents. If we look at a different network structure, so the homogeneous model, where we have P, and P ranging from 0 to 1, we in fact get the following. So we also see that in case alpha 0.8 and alpha equals 0.1, 0.8 is the black line and 1 is the blue line. Risk sharing is also doesn't have any consequences. So things get worse for the agents whenever network connectivity increases. But also here in case of alpha 1.5, 3 and 5, which corresponds to, so green is 1.5, 3 is red, and 5 is orange, you see that increasing the degree of connectivity in the network has a beneficial effect for these agents, for these individual agents too. Although more and more risk from the object gets in the system of the insurance companies. And yeah, let's have a look at it for this C alpha M, so for the value at risk of the whole system. So in the case of alpha 0.8 and alpha 3, you again don't see a qualitative difference between these two cases, as you have seen it on the previous slide. So the different colors here are just different norms, right? And it turns out that if you take the norm to be sufficiently convex, then risk sharing is also beneficial in that case of infinite mean models in multivariate sense. Okay, we can also do add some heterogeneity in the model. Just, I said in the beginning we have Pij, so we have all kinds of freedom. So we can just assume Pij to be of the form beta I and delta j, where beta I could be some measure of the risk appetite of agent I, and delta j could be measure of the attractiveness of object j. So in the first case, I look at a vector beta, which has 1 here and 0.1 at the other agents. So if the delta increases, this means that there's actually one key player in the market and the others don't really take part in the market. And what comes out for the multivariate value at risk is that it's essentially the same as if this one agent would act as just as a single agent, because it it determines the whole market structure. And there is even no degree of risk sharing because the other agents don't take part too much. Here's another extreme example. So we think of the agent 1 not really to take part in the market, but all other agents to be really active. And as the delta increases, you see that in this case, it happens again that there is this effect of risk sharing.
Just to
Yeah.
connect with the beginning of the talk, you talked about different attractiveness of different objects, but they all have the same alpha, so they're all heavy-tailed losses with the same parameter.
Yeah.
I mean, it's because of those properties that the heaviest tail.
Yeah. I
is
mean,
what matters.
no, in this case, I have put just diversification on the risk willingness of the agents, and this delta is for every step the same.
Oh, I see. You have the same delta for every. Okay.
So if delta approaches 1, it's the case that every object is insured because agent 1 has total risk appetite. So he takes part in every insurance.
So in your model, it's not interesting to consider different delta J's and different values of alpha for the object.
I mean, it's not.
Because of that
No,
dominance of the heavy tails over the weight.
No, I actually don't think so, because the attractiveness of the object might not be only determined by the alpha, but also by different factors. Okay, and yeah, let's go one step further. We look at the Rush model in the same situations, but now just with alpha equal 3 and univariate agents. So the first agent is the black line and the second agent is the blue line, so value at risk of this first agent as a key player in the market. Although we have alpha equal 3, does not decrease, so it just increases. But if you're a part of this rather non-interactive community, then you see that your value at risk approaches a maximum here and then essentially goes down in the end. So you have risk sharing effects obvious here. And the more it comes out in the different setting where you have one agent which does not take part in the market at all and another group of agents which is very active, and this is where risk sharing becomes dominant from some point on in both situations. Okay, so now just think a little bit differently and ask what happens if you don't impose independence on the objects V1 to Vd, but what is different if you would assume full dependence of the objects? And then one could essentially prove all the same theorems and all the same propositions and corollaries, essentially by replacing this constant by that constant and this constant by that constant, which is because in the case of full dependence, your spectral measure is concentrated on the diagonal. And this bold 1 just means the vector 1, 1, 1, 1, 1. Okay, and to get an idea in which sense the dependent case differs from the independent case, I have two plots here, one for the single agent and homogeneous network. And you see, okay, you start with the dependence, and if you reach the full diversified network, that means that everybody takes the same proportion of the risk any other agent takes. So you reach 1 again, but so in between the complete dependence of the V's is somehow a little bit split up through the network structure. And what you can also see here is that it is, for these intermediate network structures, surprisingly better to have a thinner tail, because this orange is 5 and this red is 3. So 3 is the heavier tail, and this black one is even the heaviest tail, and it's the lowest. And if the network gets more and more connected, you face the situation that this black one, which is 0.8, is the worst situation, and the lighter tails, in case that all agents were independent, is also quite good. But in the case of alpha smaller than 1, you're worse than the dependent case. In alpha bigger than 1, you're better than in the dependent case. And essentially the same stays true if you're looking at the whole system. So you get essentially the same plots. Yeah. So this is somehow all, and yeah, thank you.
Question?
Yeah?
You looked at a VAR as the measure on the vertical axis. Can you look at expected losses or something like that instead of VAR? Or what if these agents care not about the loss they expect, in the 5% tail or 1% tail, but instead how much they're going to be worth?
Yeah, we don't, in this whole regular variation approach, you don't look at the actual losses. If they are rather small, you just have a look at the extremal losses, right? And this is somehow, so in this situation, we cannot really determine what's the value at risk at level 0.99, and we can just give an asymptotic relation how it behaves if that goes to 0. So you don't have really a control over the actual losses. Yeah?
Okay. Well, 2 questions if I may. Firstly, well, it's an obvious question. What happens if every different kind of claim or loss has a different tail weight, so a different alpha? Does the problem then
if it just should concentrate on the single one.
So you get really rather uninteresting results if the alphas are different. It's just the heaviest claim wins kind of thing.
Yeah. So there are other types of regular variation, so non-standard regular variation techniques, where you might try to get statements beyond what I presented here for the case of different alphas.
Okay, and then the second one, if I may, how quickly do these asymptotics kick in? Can this be applied at the level of a 95% quantile and 99%?
So we had not thought about that question yet, but this is surely of interest.
Could you study it with the simulation study? Because these models probably lend themselves to Monte Carlo and importance sampling.
Yeah,
of
yeah.
larger claims.
Yeah, one should have a look at this, but we didn't yet.
So in this theory of regular variation, if you look at the results, so you said in the beginning that there's a whole class of fat tail distributions that fall under this umbrella. So you mentioned the Pareto and then some others.
Mm-hmm.
But then in the result that you show, the various results, at the end of the day, you always, in the asymptotic limit, you always have a power law, right? So is that like,
Yeah, you always
is that
have
telling the
power.
story of that if you're interested really into the asymptotics, then it doesn't really matter which kind of fat tail you're choosing because you're always going to end up in the power tail?
Yeah, somehow you have a portrait. But what we did was, in the beginning, to assume that your survival function just scales as t to the power of minus alpha. And these other types of multivariate regular varying densities might have here an additional slowly varying factor.
Okay.
And if you would have this additional slowly varying factor here, it would certainly be present also in such a setting.
So the general theorems that you mentioned in the beginning were something you applied for the Pareto case.
Yeah,
Okay.
because the point is, if you're ever interested in statistics, it's quite hard enough to find an estimate for the alpha, and it's, I mean, almost impossible to estimate this slowly varying function at all. Yeah. Okay.
I mean, one concrete model you could take a multivariate student distribution, just take the absolute
Yeah.
values and it's on the positive quotient, and
Yeah.
that the whole theory would apply to.
Yeah, of course.
And but there, whether you could sample it and you could work out, you could get Monte Carlo estimates of these quantities and compare them with the asymptotic numbers.
Yeah, so actually all these constants here are rather, I mean, I could write it a little bit different in the sense that it's a special case of, I could write it as an integral now of the norm of ax to the power of alpha, and I have here a measure, say, sigma dx, and I integrate over the sphere of Rd. So if I have independent v's, then it gets a sum, right? Because a different finitely many points where mass sits on. If I have total dependence, it just concentrated on one. This is why I have, in the case of total dependence, this A1 of alpha. And now you could think of putting any sigma for the v's, so any spectral measure for the v's, and also student. Yeah.
Yeah, so you could compute it.
Yeah, at least on the computer.
That model.
So yeah, you can simulate things in the computer view. In the general case, of course, you might not be able to give concrete formulas in terms of the PIJs, which determine your network structure, but you can simulate it, of course. Yeah.
Right, let's thank Oliver again.
Yeah.